Okay, at this point, let's summarize geometrically what we know about the function. We know we have a coordinate t naught, we have a coordinate y naught that lie on the solution curve. We have a segment with a slope v naught, which is going to be tangent to any solution curve. And we know that we're going to have a solution curve that, at least in a small neighborhood here, has a fairly constant second derivative. So what can we do to figure out a series of points on this curve? Well, one of the things we can do, of course, is we can start from our point and move along our slope segment for some distance delta t, and we know that having moved some distance delta t, we're going to have some change in y, which is approximately equal to the slope times delta t, which of course is v naught delta t. So if delta t is small enough, the curvature is not going to have changed the slope very much, and we can say that we have a new point which is approximately t naught plus delta t, y naught plus v naught delta t. Now let's see if we can get that all on the camera here. Okay, so our new point will be, okay, I think we've got it all. This is going to be our new point. This is our change in t. This is our approximate change in the value of y. And of course, this is our original y and t values. Here's our original t, here's our original y. And we can depict the situation. Here's our point, y naught, t naught. And here's our point, which we'll call y1, t1, equal, as before, to t naught plus delta t, y naught plus v naught delta t. What's the slope at the new point? If we know the slope at the new point, then we can repeat the process. We can move another delta t, predict what our delta y should be, and from that determine the coordinates of our new point. The key question then is, how can we find our new slope? Well, we know that y double prime at t naught is, well, this is known. So the rate at which the slope changes is known near the point t naught. So the slope change which I'll write as delta slope is approximately equal to y double prime at t naught times delta t. We conclude then that our new slope should be old slope plus y double prime of t naught delta t. So what's our situation? We have our point y naught t naught. We have our old slope, which is v naught. We have our new point, y1 t1, which is calculated, as we've seen, approximated. And now we know that our new slope is what? Well, it's our old slope plus the change in the slope. And that's going to be v naught plus y double prime of t naught times delta t. Now let's stop, take a breath, and see where all this came from. Remember that our coordinates y naught, t naught were given as the initial conditions, as was our original slope v naught. We made an approximation just by following this original slope for some distance delta t, some horizontal displacement delta t, and we got a new point. And we have that calculation over here. Then we went back and revisited what's going to happen to our slope between here and here. And we concluded that the slope should change by an amount approximately equal to y double prime of t naught times delta t. So now, what do we have? We have a new point and a new slope. So now we have our point y1 t1, and we have a slope v naught plus y double prime of t naught delta t. Now where did our y double prime of t naught come from? I was going to take a breath and review where everything came from. We know that y naught, t naught, v naught are given. We assumed a delta t. We got our y1 t1. Y double prime of t naught came, if you recall, from our equation. Our a of t y double prime plus b of t y prime plus c of t y equals 0. We had all the information we needed to solve that equation for y double prime. This is what came then from our differential equation. Everything else came from our assumed initial conditions. The y double prime of t naught came from all those conditions and our solution to the differential equation, and our differential equation, which we solved for our value of y double prime. We can now follow this slope for another delta t, and we can get another delta y, which is going to equal slope times delta t approximately, and that slope is going to be v naught plus y double prime of t naught, so that we're able to calculate the coordinates of a new point. That's going to give us a point which we'll call y2. And I've got these points labeled backwards throughout here. I'll have to fix that in a minute. T2, that should be T2, Y2. And I apologize if that caused a little confusion. We'll fix that. Okay, I've made some corrections, and they occurred on this page also. I had my Y and T backwards here, and of course I had it backwards throughout this page. So hopefully we've got that straight. Now, it should be clear that starting from our point T1, Y1, we can move delta T. We're going to get a change in Y, which is slope times delta T. The slope being our old slope V0 plus our change in, hang on, okay, thought something else was wrong there, but no. Our change in Y being our slope times delta T, our slope being our new slope, which we use to calculate our change in Y, so that Y2 is going to be Y1 plus our new delta Y. Now where does this leave us? It leaves us at another point which we can label, trying to do this in order now, T2, Y2. Now needing to project to a new point, and we're going to have to figure a new slope. What's our new slope? It's going to be our old slope, which was this, plus our change in slope. Now I'm not going to go to all the detail of writing that out, but here we have now another new slope. Which we can use as a basis for predicting a new point. The key again being that our change in slope here is based on y double prime at T1, and that's found from our differential equation, provided now that our A of T1, B of T1, C of T1 are defined, and that A of T1 is not equal to 0. And make the statement that our new point is always predictable our new slope is always, and I'm starting to write things badly, always, bad looking L there, but our new slope is always predictable if our functions A of t, B of t, and C of t behave themselves. And that means that these three functions have to be defined at our points and all our points in between, and A of t can't be 0 at any of those points.